Okay, so now from the magnetic fields, magnetostatics, let's talk about getting to inductance calculations. And that's because, again, as you remember, in the transmission line part of the class, we were using inductance as a parameter in our transmission lines. But we assumed that somebody would give us the inductance values, but there might be cases where we have to calculate our own inductance, and that comes um, from the magnetic field. So we're going to try to calculate inductance for a couple of cases. And as part of that, we need to use a magnetic field. So the first question is, what is inductance? What is inductance? So inductance, so I'm going to start with a fuzzy definition of inductance, and hopefully as we go, we'll sort of get a better idea, because it's hard to describe in English terms. But inductance, you can think of it as a concept that links a magnetic flux with a particular conductor or inductor. Okay. And to do that, there's a concept called flux linkage that, again, I'm gonna define it as, I'm not gonna define it as an exact idea because it's mathematically difficult to do. But for now, I think it'll make more sense hopefully it'll make more sense as we do some examples and show you guys. But so we're not going to define this, not going to define exactly from a mathematical sense. But we're gonna look at it. So let's think of what a particular linkage might be. Okay, so let's say a particular inductor might have many linkages, many flux linkages. So let's say if you had let's think about a single flux linkage. So single flux linkage. And let's say if you had sort of a magnet with a north and a south, you can think of these as having sort of lines of flux, magnetic flux. Each one of these lines is a linkage. So if you have a particular inductor, you could have a bunch of these fluxes. So let's say we define a bunch of fluxes with values of phi 1, so it'd be n1, phi 1, n2, phi 2, And when you think of it, n's might be integers. Okay, so you might have a bunch of induct magnetic flux linkages, a bunch of flux linkages. And flux linkages, or the total value, is by uppercase lambda, so capital lambda. And it's measured in units of Webers. So it's omega WB. And that is equal to the sum of all the flux linkages that are associated with a particular inductor, that are going through a particular inductor. But it also turns out that you might not have an integer number of flux linkages, but you might have like partial flux linkages. So in that case, again, I haven't defined what a flux linkage is, but it's sort of a way of looking at how an inductor is sort of connected with a magnetic field. In that case, so again, still hang on, and we're going to try to see if it makes sense for you guys in a bit. But you could, instead of having a summation, if you have the case where you have sort of a fractional flux linkage, you might have an integral of n d phi, where d phi is b dot ds. Meaning that you might have a place, inductor, and you might have a bunch of B fields going through this, and there might be sort of a fraction of a line, and this is like an area integration. So in that case, gamma is integral of n b dot ds. And in a linear medium, B is proportional to current. So if you want to think of it, if you have a case of a line with a current going through it, you might have, so in that case, B is going to be coming out like that. And we know for this, we calculated it in a couple of lectures ago. You have phi I mu I over 2 pi r is the value of B in that case. So the way you would kind of measure, or in real life, try to figure out this this flux linkage is, or magnetic field as a function of current, is you would calibrate. So you would sort of calculate the electric field for a particular current, and then that would be the same ratio of that with any other current. So if you had sort of a situation where you couldn't easily calculate the B field, you would do the ratio of the B field at a calibrated current, and then you would use that to figure out the B field at any other current. So basically you would end up with B as a function of I is equal to the ratio of the current over the calibration current and the B field at the calibration current. So if I plug this into this this flux linkage equation, that is equal to integral of n magnetic field at this calibrated value over I0 dot ds, the whole thing times I, and then this is equal to integral of I area in b I0 over I0 dot ds. And this whole thing in the integral is defined as inductance. And so that's L, and so L is defined as the sort of the total flux linkage over the current. So, okay, so that's fine, but we still haven't defined flux linkage. So this is going to be a little hard, but I'm going to try to get you some feel for the meaning of flux linkage. So let's say we start with the case of thinking about a wire that's in a loop. Okay, let me actually write it in a loop. So let's say I've got a wire and I'm bending it, so like that. So current's going in from one side and coming out the other. Okay, so, and then imagine a ring that's coming through, and where the ring is going, so basically the ring, where I've got an opening in the ring is when it's enclosing this wire. So here it's not enclosing the wire. Imagine the ring is enclosing this part of the wire. So when that is the case, we say that this has a flux linkage of 1. So this is flux linkage of 1. Okay, now don't give up yet. So now let's look at a case where you have a wire loop. So a coil. So I'm going to try to draw a coil like that. So this is a wire coil, and we've got a current I flowing through this coil. And now let's draw an example where I'm going to try to draw an example of something that has 3 flux linkages. So imagine if I draw a loop. Let's see, a loop that goes around here, goes behind that wire. That part of the coil goes behind this part of the coil, and then this part of the coil. So basically it goes behind this guy, so it captures that guy in the loop, captures this guy in the loop, captures this guy in the loop. So this guy, this particular line, has 3 flux linkages. Then let me try to draw something that has, let's see, it has 4 flux linkages, so it would be another line. So it would go around that guy, that guy, that guy, that guy. So now we've got 1 2, 3, 4. So this guy has 4 flux linkages. And then a line that would have 2 flux linkages would go here and here. So this would be 2 flux linkages. So we still sort of have a vague definition of a linkage, but sort of this is kind of what we mean, and some again it's pretty vague, but you can think of how a particular conductor, or you want to think of this as an inductive element, how it has a linkage, a flux linkage, it has linkage to a particular magnetic flux. So this is a particular magnetic flux field, and there's sort of a set of linkages to that guy. And what we're really concerned about is the average flux linkage. So in this case, you have, if this is all we have, you have 4 flux linkages plus 3 flux linkages plus 2 flux linkages, and we have 3 of these fluxes, and that's equal to 3. So that's the average flux linkage. So still pretty vague. I think we're defining things a little bit more, but still a little vague. So let's try to do an example. So example 1 is something called a toroid, which is used extensively as inductor in printed circuit boards. You see toroids kind of everywhere. And the way a toroid works is there's like a sort of like a dielectric ring. I'm trying to draw that. Oops. It's a closed ring. Let's see actually if I can see this. Oops. So can I find a toroid? Toroid, what would it be called? Let me see if PCB inductor, here we go. So it's something that looks like this. You guys probably can no longer see my pointer, but you can see there's this sort of a ring, and then there's this wire around it. So again, back to our drawing, we have a ring, and then let's say we've got an inductor around it, and I'm going to try to draw this in the form of a wire. It's gonna looks like that. So it's like some kind of dielectric with a wire wrapped around it. By the way, this they use as an inductor as part of usually it's used to filter power supply, noise, etc. So basically if you have glitches in your currents or something, it's trying to fight that. So let's say there's a current going in through the wire in and through a wire out. coming in, going out. So this is your toroid. And then so this current, because of the way the direction is, basically the magnetic field is actually going to be running inside this dielectric. Remember, the magnetic field is going to be sort of in the direction perpendicular to the current. So this was how the magnetic field is running. So magnetic field is going to be making circles in the phi direction. And now let's give some definitions, or some values. So let's say the radius of this guy, this toroid, is r, and the thickness is d, and so the radius of the solenoid, which is this shape, is r, and the thickness is d, and let's say n is the number of loops. So that's the number of these loops around this wire, the wire loops around this dielectric, and the number of these loops is pretty big. Let's just say this is a large number, and let's say that r, which is the radius, is much bigger than the thickness d. Okay, so if I was going to do a visual of the loops in some ways, if we define the number of loops as being large, you can imagine that I've got a bunch of like loops, current loops around, going around the solenoid. So then when I integrate this b sub phi r d phi over mu, so that is equal to the total number of loops times the current. So that tells you that's how much current is sort of the magnetic field is enclosing. So basically, because we've created a bunch of loops, if you define a magnetic field going around here, it's looking like, although we've got one current running, but because we've created these loops, it looks like, if you're defining this as the magnetic field, it thinks that it's got a bunch of currents that it's enclosing, because we've wrapped the current, we've created a situation where this particular magnetic field sees a bunch of loops, sees a bunch of currents, I should say, n currents, which is the number of loops, but we really only have one current running, but from the magnetic field sort of view, it thinks it's got a bunch of currents going in loops. Or so b of phi of r is mu ni over two pi r. And also the other assumption we're making is that the entire magnetic field is sort of enclosed inside here, and that's the case when the toroid is tightly wound. So you got these loops, these wire loops are tightly wound, and so that means the magnetic field does not spill out. So in other words, if this is a toroid, or this is this dielectric with this thickness D, the magnetic field is kind of confined to this area. So whoops. Field confined to this area. And this area is pi d squared over 4. Okay. So what we have here then is that, going back to our definition or concept of the total flux linkage. Okay, so if I plug that into this, it's going to give me total flux linkage, assuming nothing leaves the loop, is N B sub phi pi d squared over 4, and this equals to N mu sub Ni over 2 pi r pi d squared over 4, and that's equal to mu n squared I d squared over 8r. So if that's the case, then the inductance of this toroid is the total flux linkage divided by the current, is equal to mu n squared d squared over 8r, which is basically the inductance of toroid. So again, this toroid thing is something that's used in your printed circuit boards, etc. It's an inductor that is typically used to filter power supplies, and basically you're basically creating an inductor by wrapping this wire around this sort of solenoid structure, and basically you can determine the inductance or design in the inductance by controlling the thickness of the toroid, the radius of the toroid, and the number of loops that you have around the toroid. So that's one example of an inductance calculation. Now let's look at another example. So example 2, we have a coax cable. And again, we have, so the cross section of the coax cable, we have the center has got a radius A, the outer shell has, do 2 of these guys. Okay. So this is the outer metal. Okay, and that's B, that's C, and you have a current of I in the inner conductor and a minus I in the outer conductor. So again, you'd have to have a bunch of different sections. And we'll see that the flux linkage will only be complete. So we have this section, we have this section. We saw this when we did the magnetic field calculations. And then we have the third one is we have the shell section, and in a perfect coax cable there's no magnetic field outside, so there's really 3 sections, and we'll see that the flux linkage will only be complete in one section and will be incomplete in the others. So just as a reminder from the sort of the magnetostatic lecture, in the case of R being in the inner conductor, the magnetic field there was mu I R over 2 pi a squared. In between in between here, it was B as mu I over 2 pi R, and inside this outer conductor, so R being between C and B, it was 2 pi R over mu B was I minus I R squared minus B squared over C squared minus B squared. So now let's think about the surface we need to define for the flux linkage. Okay, so this is gonna get a little bit complicated thinking about the surface. So let me draw this way, a coax cable. Again, this guy, the center line, this guy is A, and we've got B and C. These are the other dimensions. Now, and the current's going this way. So since the current's going that way, our magnetic field lines are actually going to be going in sort of like that around the inner conductor. So if we want to figure out the flux linkages, so flux linkages are defined as points where the magnetic field is kind of crossing once, okay? So with that case, that sort of that surface where we're going to define for the flux linkage has to look like something like, let's see, something like this surface like that. So this is a surface where this magnetic field is going to cross once. So this surface will be crossed once for each one of these magnetic field lines. So from there we can get the flux linkages. Okay, so in the case, so in R is being less than A, okay, N is equal to R squared. The number of flux linkages are going to be R squared over A squared. In the case of R between A and B, flux linkage is going to be 1, so entire flux gets linked. And in the case of B being between R and C, N is equal to 1 minus R squared minus B squared over C squared minus B squared. Okay, so basically, let's see here. So then the sum of the flux linkages are going to be, so we have the case from 0 to A, mu sub I, R over 2 pi A squared, R squared over A squared LdR, plus from A to B mu I over 2 pi R L dr, and then plus B to C, and basically I'm going to be looking at this thing, so I'm not going to write that, so I'll just write it like that. Okay, so basically remember that inductance is going to be this total flux linkage divided by current. But in the case of the transmission lines, we want to figure out, so that's inductance is flux linkage divided by the current. But in the case of transmission lines, we're interested in inductance per unit length. So we do L over the inductance over the length. So this is current over length, and this is equal to mu over 8 pi plus mu over 2 pi natural log of B over A. So basically these are like sort of figuring out these integrals, plus mu over 2 pi c squared over c squared plus b squared natural log of c over b minus c squared over c squared plus b squared plus 1/4 c squared plus b squared over c squared minus b squared, and all of this is in units of henries per meter. So that's kind of the total, and basically, I mean, it looks sort of, this inductance looks somewhat complicated. Did I do this right? Yeah. So now, fortunately, it turns out that this part is usually negligible. In value. So you basically end up with this being the sort of the value for the inductance per unit length for a coaxial cable. So those are just some examples of inductance. And hopefully by the end of it, the flux linkage made a little bit more sense. Again, it's a concept that you need for inductance, but it's kind of hard to explain. But hopefully the examples showed you what they